Hello, this is Jonathan, and today I'm going to be talking about the existential typeclass antipattern. However, I'm not going to be talking about it in terms of Haskell, but I'm going to be talking about whether or not it applies to Rust. So over here on the right, I have an article written by Luke Palmer. It's about this existential typeclass antipattern in Haskell. And essentially, the problem here that Luke is describing is that people are using existential type classes far more than they should be. For instance, he has this widget example from some library, VTY UI, I believe. And essentially, he's saying that this is far more complicated than his approach. He has a more straightforward approach, and the API of this is a bit more awkward because he has this any widget thing here. So down here, he talks about how you can turn this type class, you can rewrite it as just a single struct. So in Haskell, this is called a record type, but since we're going to be talking about Rust, I'm going to be talking about structs. So I'll talk about the translation a bit later, but for now, I think the most important thing to talk about here first is the difference between universally quantified types and existentially quantified types. So here I have this function that so we're going to try and write a function that returns something that implements an iterator, for example. A naive solution might look something like this. If we try to run this, you'll see that this actually doesn't even compile as a mismatched type. And the reason for that is because t is actually universally quantified. Now, typically, if you didn't have a trait bound like this, it would just mean that, okay, for all types of t, we're just going to return that type. But because we have a trait bound, we're going to say that for all types that implement iterator, or whatever, we're going to return that type. And essentially, how generics work in Rust is that if you call a generic function like this with an actual specific type, like say int, well, int won't work here, but maybe, I don't know, like a flat map struct would go into here, then it would just copy and paste this function and replace all instances of t with the specific type. So it would just like return a flat map here. So essentially, this function implementation has to work for every single type there is. Well, as long as it adheres to the trait bounds. So in this case, I can't actually really implement this function because we have to return all types that implement iterator. That doesn't really work. I can't really do that in any way. This doesn't work. So what you'd actually want to do in this case is have something that's existentially quantified like this. So this is using the somewhat newer impl trait feature. Here we're saying that we're returning some type that implements iterator, but we don't know the actual specific type. So what's nice about this is that, well, for one thing, it actually compiles. So if I do this, yeah, you can see that this entire thing compiles. But the other thing that's nice about this is that we can change the concrete type that we're returning here. As long as that concrete type returns or implements iterator, then we're okay. We don't have to change the signature of this function at all. Now, this doesn't mean that you could have like an if here. You can't go like if blah, then return, I don't know, like some kind of string iterator, right? You can't do that. All the branches have to return the exact same type, but it does mean that you're not tied to you're not forced to update this every single time you decide to change the concrete type here. So that's quite nice. Aside from this approach, there's also the box approach that I've seen pretty often. So if you do this, essentially you're going to be using a trait object instead. So iterator, instead of being a trait, is now a trait object. I think actually if you're doing stuff like this, they in the Rust edition 2018, I believe, they actually have support for this like dyne keyword that indicates like dynamic dispatch, so you can also add that as well. I think that's you can actually configure Rust C to force you to add that, but I'm just gonna ignore that for now and just say that yeah, this is a trait object. It works pretty much the same way. You can use trait objects to represent existentials, or you can use impl trait. It's pretty much the same thing. Doing this also makes this a trait object, but of course, because you're using a reference, you're gonna have to worry about lifetimes. So, because usually when you have a box, you can like take ownership of things, and that's a lot more ergonomic. It's a lot easier to work with boxes. Of course, you have to pay the extra cost of having stuff be allocated on the heap. So, yeah, so it's an extra layer of indirection there, and the extra cost of having to allocate and deallocate memory. So yeah, that's pretty much it for the universal and existentially quantified types. Now I'm going to move on to the actual translation of this code. So if we come back up here, what they've done in Haskell is they've defined a widget type class that has a render method and a grow horizontal method and a grow vertical method, and just basically a whole bunch of other methods. I decided to take things in a bit more of a simple approach. So they copied their example from VTY-UI. Because I'm not using a real example, I'm just kind of doing a demonstration here. I decided we'll just roll with render and grow horizontal. So for those who are not really aware, people commonly compare Haskell's type classes to Rust's traits. So it's pretty much a one-to-one mapping here. Obviously, instead of using W, I'm going to be using self instead, because we don't need to have the extra type parameter. But yeah, it's a pretty small difference. I'm going to ignore the any widget stuff. It's something that I believe the author actually commented on this post and said the any widget was supposed to be used for like list types. It's not supposed to be used for whatever else. So I'm going to ignore that argument, simply because it doesn't seem like it was really intended to be used in the way that the author was using it here. But anyway, so I added a window struct. It's kind of similar to how they have these like, well, they have these like datas here. They have like data text, data box, data fill. These are all different widgets. So I have window. I also have a my widget, and here they create instances for their widgets. So that's basically the same as these impulse. Impulse is the same as creating a type class instance. My type class instances here, or I guess my trait impulse, are pretty simple. Here I'm just like creating an image. An image is defined up here. It's just a struct with a U32. It's nothing special. It's not really an actual image, of course. And I have a display region struct as well, which is also kind of a dummy. It's not really being used. In fact, I could even throw this on here and it wouldn't really change anything. Actually, the compiler would be like, it wouldn't complain about this. Grow horizontal is a very trivial function that just returns true. Same kind of thing going on for my widget here. So I've got image with the value being 1 instead, and grow horizontal is now false. So here is what, right up here, this is what the proposed solution is, and I've copied it down here. So in contrast to the type class up here, we're just using a regular old record type. I'm using a struct on this side, on the Rust side, and basically for each method that was defined on the trait here, we're just gonna turn it into a field. So what's nice about Rust is that it does have support for lambdas. Actually, I think like almost every other language I can think of at this point does have some support for lambdas. But yeah, here I've got a function pointer. You don't have to make it a function pointer. You could actually do something a little bit more generic, like using like the fun traits. the various fun traits that Rust has. So something like this, and then replace all this with T. But by all this, I mean all this. But I'm not going to do that for this demonstration. That approach is a little bit more flexible because it gives you more types of functions that you can pass in. Specifically, this function cannot ever be a closure because it's this concrete function pointer type. So that's an important distinction to remember. But anyway, aside from that, we can get rid of any reference to self. So remember how we had these self arguments here? We don't actually need those anymore. There we go. And so that function that originally returned a Boolean here, grow horizontal, it just ends up being a field that is, well, just a Boolean. And it kind of makes sense because in the original implementation the function just returned true, right? So what we're going to do instead is when we construct a widget, or widget 1 as I've called it here, we're actually just going to give it the implementation on construction. So in this case, for ergonomics, I created my own freestanding functions here, like my widget render. So I'm going to be basically implementing widget, or widget 1, I guess, for my widget by creating a new instance that defines render as my widget render and gives a grow horizontal value of false. So yeah, that's pretty much the gist of it. I've heard this referred to as manual v-tabling, I believe. I think someone mentions it in the comments of this article here. But yeah. The other thing I want to talk about briefly is these froms. This was just for ergonomics. So if you don't know, in Rust, there are from and into traits, and if you implement the from trait, you get an automatic implementation of the into trait, which is nice for just converting between types. I've used it down here, yeah, in this commented out code. You can see I'm calling .into just because I wanted to have a vector of widget 1s and want to, have to actually write my own conversion functions and actually explicitly call those. I mean, I guess that is kind of technically what I'm doing anyway, but at least I'm using like the more idiomatic API for it, I believe. So yeah, last thing I want to do here is actually run the example. So actually, I think I've already run this, but let me just run it again. Yeah, so we can see here that I'm using the first implementation with the widget type class. So this is actually just a widget trait object because I have to box it. I can't have this heterogeneous collection of window and my widget because they have different sizes. As you can tell, this has like a tuple. This one doesn't. And even if I did have like a U32 and U32 here, I'm pretty sure the compiler can't really, make any decisions like, oh, these are the exact same size, so therefore I can just, do whatever. The types are completely different. So yeah, I'm boxing here. You don't technically have to box for this to be a trait object. As I've mentioned earlier, I could have just passed a reference, but then these two objects would have to actually live like out here because otherwise the lifetimes won't work out. It's a little bit less ergonomic, and I just wanted to be able to take ownership. Actually, let me just undo that. Yeah. So this is just the easy, more typical solution. In fact, I believe this is what the Rust programming language book does as well, as an example of dynamic dispatch. So yeah, that's pretty much it. Here's the loop that iterates over the widgets and just calls render on them. It's nothing special. So now we're going to run the other program. And it pretty much just does, well, the exact same thing. Oh, it doesn't compile because I have to do this. Yeah, so Rust C is complaining that this was being used as a method, and obviously widget 1 doesn't have a method called render because we turned it into a field. So in order to say that it's a field that can be invoked, I have to wrap it in parentheses first before I pass in the argument. So yeah, Rust is very explicit about these kinds of things, which is it's kind of nice. But anyhow, I've basically called into on each of these types. This is what Luke suggests in here, because he has an example of where he has like the window data, and it's like, what if somebody else made a widget type which did use the additional assumptions of the separated data types provided? So he's trying to prove that this is still a perfectly valid approach. You just need to define a toWidget function that converts your window into a widget, and that's basically what I've done with the into function here with these from impls. So yeah, now I guess I can actually talk about the trade-offs. So first of all, the obvious one is I don't have to do this box if I'm using the approach that Luke suggests. So that's quite nice. I mean, even if I wasn't using a box and I was just, you know, using a reference. Actually, you know, the reference, you know, I'm not entirely sure. Yeah, I'm actually not sure about the performance trade-offs here. So the reference is a little bit less ergonomic because you're not taking ownership of the items in the collection. So in my opinion, that's kind of meh. I mean, it's less overhead than the box. And here we just don't have the box at all, and we can also still, you know, take ownership of things. And on the other hand, this is still like a box is still a pointer, right? It has like a fixed size. These items have a fixed size as well, but I mean, it depends like how many methods or not methods. Well, how many methods were on the trait, right? If we had a lot more methods on the trait, we'd have a lot more fields on the struct, and therefore our vector here would have items of much larger size, and we might not actually want that, because that could also tank performance as well. So yeah, there are some performance trade-offs here. I'm not really sure what's best. I think it just really depends on what situation you're in, right? If you have like a relatively small struct, then yeah, this approach is probably fine. You can get away with this and avoid the boxing, but otherwise, yeah, you might want to actually use the box. The other trade-off is this approach irreversibly converts a window into a widget 1, which is kind of shown here, right? Like once you're a widget 1, you're in like a heterogeneous collection, so you've lost information about the specific types, and so yeah, it's completely irreversible. This might not be a problem. It really depends on your use case. But yeah, it's a slight loss in expressivity. So you really do have to consider your options here. It's not like one approach is strictly better than the other. So, what's the verdict on this? Is this article, is this Haskell anti-pattern thing relevant to Rust? And the answer, in my opinion, is that yeah, it is actually kind of relevant. Maybe not for the same reasons as it's relevant to Haskell. I mean, here you actually have like explicit boxing and stuff. But yeah, I think it is relevant. One thing I want to note is that closures and just Lambda functions in general in Rust have different ergonomics than in Haskell, obviously, and they work in a very different way because of move semantics, right? We have like fun mute, and we have fun, and then I forgot the last one, fun once. So yeah, there's it's a little bit more tricky to work with them in Rust. So this solution might not be so ergonomic in some cases. So yeah, that's pretty much all I had to say about this. If you have anything that you have to add about this topic, then please leave a comment in the comment section below. And thank you very much for watching.